All right, our next speaker. Is it okay?
Sound correct? Oh, okay, okay.
All right, so let's welcome Weijie Wang from Yale University. He will talk about dynamic SNARKs.
Okay, hello everyone. So my name is Weijie Wang. Today I'm going to introduce dynamic ZK-SNARKs. This is co-advised with co-authors Haralampers, Shravan, and Dimitris. So first of all, we all know ZK-SNARKs. This is a tool which allows us to prove a statement without revealing anything about the witness with a short proof. With some motivated by some application I will mention in the end, our goal is to build a data structure for SNARKs. So briefly speaking, I want to build a SNARK plus some dynamic updates. This is because sometimes when we have a SNARK proof and we just modify the statement or the witness a little bit. But but in this case, we need to recompute the whole proof from scratch. So can we build some data structure so that we can dynamically update the proof? So briefly speaking, the definition of dynamic ZK-SNARKs is the vanilla SNARK plus one update algorithm, which takes as input the old statement, the old witness, the new statement, the new witness, and the old proof. It outputs a new proof, pi prime, maybe with some auxiliary information, which is from the data structure to help compute the new proof. And one constraint of this update algorithm is the runtime of this algorithm should be sublinear to the statement size or witness size, because otherwise it could be trivial. We can just recompute the proof from scratch using the proof algorithm. To be honest, before our work, most existing SNARKs are not dynamic. So, for example, Planck, Spartan. So they are all built upon PIOP and polynomial commitments. So in their protocols, after the verifier picks some randomness, the prover needs to do some computation after based on the randomness. So if you just change the witness a little bit, then the prover will receive a new randomness from the verifier, and every computation after that will be discarded and recomputed. So in this case, randomness often leads to linear recomputation. And also in some situations like Growth 16 and some other protocols, there are some polynomial division occurred. And in this case, for example, for Growth 16, you need to compute a quotient polynomial. And if you change the witness a little bit, then the quotient polynomial also need to be recomputed in almost a linear time. So these reasons could lead to linear recomputation for existing SNARKs. So in this work, we present Dynaverse and Dynalog, which are the first dynamic ZK-SNARKs, and they are all in the universal settings. And you see there's an update algorithm, and for Planck, the update is unavailable because it needs n-log-n recomputation. And for both Dynaverse and Dynalog, the update algorithm is sublinear to the statement size. And I want to mention that for Dynalog, although the update algorithm looks good, but we need the QASDBP, which is the same assumption required for GIPA. I also want to mention that there are two follow-up works after our work. One of them is for dynamic Growth 16 protocol, which also will appear at Eurocrypt this year. And another work is for designated verifier dynamic SNARKs, which remove the GIPA here, but the requirement is the verification is only designated. So it's like a balance and some trade-offs between them. So to introduce our construction, let's look at the NP relation circuit satisfiability problem. So basically, this is just a small variant of the Planckish arithmetization. So we are looking at the circuit satisfiability problem. So for this NP relation, the public statement is some public whiles of the circuit. And we just, to make things easier, we just assume that gate number 1 to number n is addition gates, and gate number n plus 1 to 2n are multiplication. And so there are 6n whiles, 3 per gate. And so there are 2 constraints for this circuit is satisfied. The first one is every gate is correctly computed. So if it is an addition gate, the left input plus the right input should be equal to its output. If it is multiplication, then it is multiplication relation. Also, since each gate has 3 whiles and there are 6n whiles, we need to show that each while is correctly connected. And this is done using a permutation, which indicates that, so for example, sigma 1 is equal to 2, which means the first while is connected to the second while, and they should be equal. And this can be characterized with a permutation. And as long as each z of I is equal to z of sigma of I, then the while constraint is satisfied. Okay, so we are building SNARKs, dynamic SNARKs for this circuit satisfiability NP relation. So our basic idea is to decompose the permutation I mentioned in previous slide. So basically speaking, our goal is to prove z of I is equal to z of sigma of I for every index. And for permutation arguments we know so far, like what we did in Planck, there are many randomness incurred, and as I said before, if you just change 1 bit of the permutation, then everything should be recomputed. So what we do is try to decompose this permutation. So consider picking any vector z1 to zk, any arbitrary vector of the same length. Then it is equivalent to show that there exists some vector h1 to hk such that the subvector or the partial vector z of j at the location I is also satisfies this. So basically, for one direction, we can just pick arbitrary z and compute such h from this equation and show the existence. And for the other direction, we can just, since we know that there exists such h1 to hk, the sum over such k equations will get to the left hand side. So these two statements are equivalent. So the basic idea is we pick some proper decomposition of the witness vector z. Then we deal with z1 to zk separately for both gate constraint and the permutation constraint. So our main contribution is we build dynamo, which is a sparse argument for the relaxed permutation relation. So the relaxed permutation relation is just what we need here. For any specific j, we can show this relation based on some fixed permutation. So basically, our contribution is as follows. We decompose the vector z as we want, and we use dynamo, which is a sparse argument for the relaxed permutation relation for each z1 to zk. And then we find some other approaches to deal with the gate constraints. So that's how we build dynamic SNARKs. For Dynamo, I just want to mention that this is a sparse argument. So the sparsity here means the approval time of this small snark of this argument should be linear to the Hamming weight of the statement and witness side. So basically speaking, if we do some decomposition of z, then the sum of the Hamming weight of each z1 to zk should be equal to n. So for example, we have square root of n, k is equal to square root of n, and each of them has Hamming weight square root of n. Then if we just need to update one of them, then the update time or the computation time for one Dynamo proof should be linear to square root of n. Okay, so I will not go to the details of the construction of Dynamo, but this is just what we need as the basic building block. So to build dynamic SNARKs, so what I will present next is I will present two decomposition of the z vector such that we can make use of the decomposition to build dynamic SNARKs. The first decomposition is we are going to build a weakly dynamic SNARKs here. So a weakly dynamic SNARK means we fix the initial statement, and every update will be computed based on this initial statement. So for example, we have the initial statement z, and we call it as an anchor. And we can build an initial proof, which is similar to the Planck proof. We can use Dynamo for the whole vector z, and we can use some tricks similar to Planck to build the proof of gates, which can be computed in n log n time. Then, whenever there's an update, like we modify k arbitrary locations, z prime is considered as the difference vector, and z star is the new witness, state and witness pair. So basically, z prime, which is z star, the new statement is considered as z plus z prime, because z prime is the difference values. So if we modify only k locations, so z prime should have Hamming weight k. Right? So, okay, and we specify the set of modified locations as S, and which has size k. Then, what we do here is, first, we compute a Dynamo proof for z prime for permutation relation, and it should be able to compute it in order of k time. And so now we need to consider what we need to prove right here. So we need to prove the gate constraint and for the while constraint. So now the Dynamo proof for z in the beginning plus the Dynamo proof for z prime is sufficient to show that the new statement z star satisfies the permutation relation. So what we left to do here is to show that all the modified locations still satisfy the gate constraint, like the plus, the addition, or multiplication. So what we left here is proof of gates for every location in the modified set, and show that as long as this gate, some value related to this gate is modified, then it still satisfies the gate constraint. Because the main point is, outside S, every gate is satisfied. We have already proved that in the initial proof. So for this part, we may need some commitment to commitment to the modified values and to compute some. No, it doesn't have to be. I just put it in this way to make the figure easier to. Okay, so basically, for this part, we need some commitments and some quotient polynomials involved to do the computation. But the main point is, this part of proof should also be like almost linear to k. Okay, so this is a weakly dynamic SNARKs based on some fixed anchor z. So if we like keep so the point here is, if we like modify like k more locations, then the proof should still be computed based on the original anchor, and the proof time is linear to all the number of modification locations. And everything here I listed here should be considered as a pi star, which is a proof for the new statement and the witness, but still is constant size. And this naturally gives us a sparse SNARK construction. So for sparse SNARK, so it's most of the whiles are zeros and some is non-zero. Some of the whiles are non-zeros. So basically, the anchor should be considered as an all-zero vector. And yeah, this gives us this is a direct application of this protocol. So to build Dynaverse, we use the weakly dynamic SNARKs, as I mentioned before. So whenever we have some modification based on the anchor, let's examine how many locations we have already modified. So if k is smaller than square root of n log n, then we just compute a pi star as I described before in order of k time, which is at most the square root of n log n. If k is larger than square root of n log n, then we set z star as the new anchor and recompute everything from scratch. So this recomputation requires n log n time. And now we can, for the following updates, the number of updated locations should start again from 0. So whenever we need to compute the pi star based on the anchor, the computation time should be at most order of n log square root of n time. And the amortized time to do the recomputation is also like similar to an order of square root of n, because we only do the recomputation every square root of n updates. And I want to mention that this recomputation can be de-amortized based on some standard tricks. Okay, so this is the first construction, Dynaverse with square root of n update time. The second construction is Dynalog. I will not go to details, but I just want to show some intuition how we achieve this. So this is built upon some standard waterfall technique, which is similar to the hierarchical ORM. So basically speaking, we have log n levels of exponential size. And whenever there's an update, we log the update to the smallest available level. And yes, and each level we will have a dynamo proof. So for each level, there are some records of updates. So we can build a sparse vector based on the updates. So basically, this can be considered as a decomposition of log n vectors. So each level also has a proof of gates for the updated locations. And in this case, with some de-amortized tricks as well, then we can make the update time polylog. And to make this work, we need some GIPA to aggregate the proof. Okay. So now I'm going to introduce some application of for this protocol. Some of the applications are discovered recently, so it might not appear in our submitted paper, but so for example, for this application, it appears, as I said, in one of our follow-up works. So this is called dynamic proof of index. So sometimes we have a vector A, and it has two commitments, C and C prime. So C is like the Merkle root of the original vector, and the C prime is the Merkle root of its sorted version. So we need this like, so for sometimes we need the sorted version as an index so that we can do some binary search or some similar stuff in databases or so on. So to make sure we can make use of that sorted version, we need a circuit to show that the sorted version is correctly committed. And we can build a SNARK to show that. And the point of such circuit is whenever there's an element in A is changed, we want at most polylog of numbers, polylog number of whiles is changed in this circuit so that we can compute, we can use sublinear time to recompute the proof. So for example, let's consider the application in verifiable databases. The server wants to show that the server wants to do a binary search for a vector, which is a database. And the server by itself computes the index, which is a sorted version of the database. And the server computes the commitment, which is of both the original database and the sorted version, which is C and C prime. To show that the server conduct a valid search based on the sorted version C prime, it needs to show that the consistency between the original commitment and the sorted version. So to do that, the server can compute a SNARK proof to show the consistency between them. The problem is the database could be changed over time. So whenever the original vector is changed, the server needs to compute a new proof to show that it's consistent between the old digest and between the digest of the original vector and the digest of the index. So with this dynamic proof of index, as long as this circuit, like circuit itself, changes at most polylog number of whiles, and we have a dynamic SNARK to support sublinear time to recompute the proof, then we can update the proof of the consistency between two digests in sublinear time. So this is the first application I want to mention. The second one is for passwordless login. So for example, to access a blockchain account, we can use OIDC like Google to help us log in. And Google basically signs some JWT token which binds the ephemeral public key from the user and the blockchain address from the app. So the app itself may need to compute a SNARK proof to show that I know a token signed by Google which binds EPK and the address. So for multiple logins, the EPK could be changed over time somehow. Then in this case, we can just update the proof. We don't need to recompute everything. And the DApp can just use the updated algorithm to generate the new SNARK proof to finish the login procedure. And from an ongoing preliminary experiment, we find that if we just change the ephemeral key, public key, then around like 25% of the wires is changed. So we hope, based on some dynamic SNARK protocol, then we can beat some previous works by just compute everything from scratch. The last application is for bounded step IVC. So basically, we try to build an IVC protocol without SNARK recursion. So the main point of this circuit is each iteration just involves some some wires change in this circuit, and we can just update the proof of circuit to generate the proof for the new iteration. I will not go to the detail of this circuit, but if you are interested, you can go to our paper to find more details. That's all. Thank you.
All right. Any question for Weijie?
So let's say I'm an adversary who doesn't know all of the witness. I only know the parts of the witness that can be updated. Can I replay a previous proof and just update those parts and not need to know the whole witness?
Yeah, unfortunately not. So in current...
Well, I don't view that as unfortunate, because I would view that as an attack.
So basically, we will put the whole original witness in the auxiliary information as part of the data structure so that we can compute. But we discovered that for some specific circuits, like we will only update the wires once or some. So for some special case and some special circuits, it could be achieved if you don't know some older witness.
I'm not sure you understood the question. I wasn't asking whether it was... I wasn't viewing it as a feature that you might not need to know the witness. I was viewing it as a potential attack.
It's a requirement for our construction for now, but we haven't considered to view it as a feature or not.
Okay, I'll have to read the paper in more detail.
Have you considered that a case where maybe updates have a special structure?
Yes.
So maybe you want to say, I don't know, this subcircuit is updated.
Yes, we believe if the update has a specific structure, then we can definitely build better dynamic SNARKs. For example, we have considered the case that updates can only lies in a fixed set of locations, or the updates can only so each wire can only be updated once, or some specific structure like that. And although we don't put such cases in our paper, but we believe we can have much better protocols if the updates have a specific structure.
All right. No more time for questions. Let's thank Weijie again.